All right. We are here for another day, and my anticipation is this is going to be one of our more difficult days that aren't the proof days. So this is a concept that the book stars as an advanced topic to give you a sense of what to expect for the day. But it's a very fun one in that we had talked at the end of last class about reducing DFAs. We asked if this DFA could be reduced, and we certainly found that it could be somewhat reduced, but we didn't see that it could be reduced all the way down to 3 states. There were some very good arguments presented in class about why we could get away with removing chunks of this, and you were right. Question?
How much has to do with like input and output states to evaluate like equivalent nodes?
Yeah, we will be looking at pairs of states, basically. The way we're going to tackle this is we're going to be looking at pairs of states and saying, on every possible character from here, regardless of how we got here, if we end up in the same level of finality is going to be very important for this, then we're going to label distinguishable and indistinguishable. And we're going to be trying to find indistinguishable pairs. And if we can find indistinguishable pairs, then we can remove one of them. So we'll get into that. The quick announcement for the start of class that we have an assignment due tomorrow. We talked yesterday about exam coming up on the horizon. It's still on the horizon, but the horizon's getting closer on a daily basis. So you'll have a study guide by Friday. And the day before the exam, which will be a week from Thursday, we will spend, I have no content plan. We'll just have a review period. And I expect people to come with enough questions to fill that period. Otherwise, I start staring awkwardly at people until they come up with questions, whether they're related to class or not. So that class will be very important, I think, leading up to the first exam.
That's Monday.
It'll be
after the study guide.
It'll be so study guide is released on Friday. The review period is the following Thursday, and then the exam is the day after that on Friday. So you have a whole week with the study guide to prepare for the exam. Other questions before we dive back into finding the minimal DFA? All right, let's do it. We're going to define the concept of indistinguishable. Basically, if from either one of those states, if for any string that we could get of any length ends in the same level of finality, then those states are indistinguishable. Regardless of how we got here, if any string from the state to the end of that string results in being in at a state of the same finality, either acceptance or rejection, then those states are indistinguishable and can be combined. So notationally, we would say the transition from P on W is either and Q on W for all possibilities. So if the finality of, I don't want to state this. I'm going to use some logic. For all W, based on if P leads to finality, then Q on that same W, these are 2 different states, leads to finality. And on those same 2, if for a particular W, if that leads to not a non-final state for P, it also leads to a non-final state for Q. So 2 different states, P and Q. For every possible string W from that, you end up in the same level of finality. If P leads to a final state on W, then Q leads to a final state on W. If P leads to a non-final state on W, then Q leads to a non-final state on W. That's the logic of it.
Put those are the same sequence.
The same, yeah. These W is the same and these W is the same. So on a particular W, this implies that. On a particular W, this implies that. If that's the case for all W, then the states are indistinguishable. We can state that they are distinguishable if we can find some string such that one of these is not true. If we can identify a W such that P leads to, on that W leads to a final state, and Q on that W leads to a non-final state, or P on that W leads to a non-final state, and Q on that W leads to a final state, that becomes an example of a way to show that these two states are distinguishable. So one of these questions is easy and one of these questions is hard. Which is which? Yes, distinguishable is easy, indistinguishable is hard. Why? This requires an example, you to find one thing. Once you find that one thing, you've proven that these two states are distinguishable. This requires an argument that says, for every possible W, and there are an infinite number of them, this holds. So we are caring about indistinguishable states because we want to combine those states. But we want to tackle this problem from the easier perspective of identifying distinguishable states rather than indistinguishable states. So we care about this, but we're going to get at it through this because this is easier. So that just goes through and shows what distinguishable means. If there are two states, P and Q, such that on W, one of them leads to a final state, one of them leads to a non-final state. Of course, then, via logic, we can show that any given pair of states is either distinguishable or indistinguishable. This ends up being difficult. So the goal of this whole algorithm is to find and combine all indistinguishable pairs. And if we can do that, then if there are no further indistinguishable pairs left, we have the minimal DFA. No two states could be combined because it would create a different logical outcome. It would represent a different language. So to move on, we're going to, how do we find those distinguishable pairs? So the first process is usually useless, any inaccessible states. We saw on the very first example that there was a state, I think it was Q5, that couldn't be reached. If you have a state that can't be reached, then we can just remove it from the DFA. It is very unlikely that you will produce a DFA in this class with such a state or see something with such a state. Although if you're reading in an arbitrary graph and manipulating that graph, maybe one of those states becomes inaccessible as you apply some logic to that graph. So maybe that then becomes the input to this. So it is worth checking for inaccessibility. In code, how do you do that?
Statement that is never true.
You keep track of a visited list. And then you can ask for it, starting with some vertex that you know is part of the graph. You just say, all right, what are all of your neighbors? Add them to a queue, add them to the visited list, and then just go through the queue, dequeue from the queue, ask, what are all of your neighbors? Add them to a visited list. And then at the very end of that, check for any vertex. Once the queue is empty, are there any vertices in your graph that were never visited? If they weren't, they're inaccessible. So next, we're going to go through all pairs of states. So looking at all pairs of states, if one of those is final and the other one is not final, we know they're distinguishable already. Consuming 0 characters of input or using a W that is just the empty string, we end up in different finality from the two states because they themselves have different finality. So we know they're distinguishable. Then we are going to enter a loop. We're going to iterate all pairs of states and all possible characters in the alphabet of the language. As we do this, we're going to transition from these two states, P and Q, that we're looping for every possible pair of P and Q. We're going to say now, imagine consuming the current character in the alphabet as an input. Where do you end up? Do the destinations for that have distinct finality? Is one of them final and one of them non-final? So we're going to ask whether those are distinguishable or not. But note that, so this is the last time I'm going to talk about finality, because we stated that everything for finality is basically here. The states themselves have different finality. But now we're going to ask, are the destinations of this, once you consume that character from an input, are those distinguishable? If they are distinguishable, then we can show that P and Q were distinguishable. If not, no conclusion can be drawn about P and Q yet. We're going to keep our states in what we're going to call equivalence classes, where we have not yet shown that they are distinct from each other. And as soon as one of these equivalence classes becomes a single state, then we know it's distinguishable from all other states, and it needs to be its own state. If we go through this process, then this will mark every pair of distinguishable states. We will continue to do this because we will continue to identify, as we go through this loop, some pairs that are distinguishable from each other, which means that when we loop back again, there's more information about which states are distinguishable from each other for the next pass through this loop. It's only once we go through this entire loop and make no changes to the distinguishability of any states that we can terminate. I will give you an example because this is a lot to take in on just a kind of a pseudocode logic type of slide. The final conclusion, once this whole process terminates with making no changes, any remaining pairs must be indistinguishable, because logically they're either distinguishable or indistinguishable. This process is going to identify all of the distinguishable pairs. So all pairs that remain at the end of that process must be indistinguishable. So again, we're answering that difficult problem by tackling it with the easier problem. And then saying everything that is not distinguishable, shown to be distinguishable by this process, must be indistinguishable because logic. They're either one or the other. So let's get you an example. Any questions on how this is worded before we hop into an example? I think there's juice in blue. Maybe not, we'll find out. Here's our example. The question for this would be either reduce the following DFA or can the following DFA be reduced? If you have either questions in that kind of wording, then you're going to want to use this process or this algorithm to go through and find whether there is a DFA with fewer states. So we are going to attempt to find all of the distinguishable pairs in this DFA. So let's walk through the process a little bit. So step one, there are no inaccessible states. We would look for all simple paths, and we would find that every state is reachable via some number of zeros and ones. We can get from Q0 to Q1, Q0 to Q3. So we can get to Q3, we can get to Q2, and Q4 we're already done. Step two said we're going to split the states into equivalence classes based on their finality. So we're going to go back to this and we're going to say, okay, we're going to make two classes. The first class is going to be all non-final states. So that's Q0, Q1, and Q3. And the other class is the final states, Q2 and Q4. We know that everything in here is distinguishable from everything in here because on the empty string, you end in different finality. Let's pick the pair Q0, Q2. Consuming the empty string, do we end in states with different finality? Yes. So we're good. Once we start thinking about longer strings, we're going to have to ditch the concept of finality and just use these equivalence classes. But we start making these equivalence classes based on finality. So now we're going to start looking at pairs of states that are in the same equivalence classes. We never need to look at pairs of states that are in different equivalence classes. We've already shown that they're distinguishable. So we're going to look at Q0 and Q1, Q0 and Q3, if they're still in the same equivalence class. After doing that, Q1 and Q3, and Q2 and Q4, with the goal of finding a way to show that they are distinguishable. So let's look at Q0 and Q1 on reading a 0. So imagine person A is here, person B is here. What happens? Where is A and B when they consume a 0? A moves to here, and B moves to here. So the people who were here and here are now there. The question now is, are Q1 and Q2 in different equivalence classes? Q1 and Q2 are in different equivalence classes. So this shows that on a 0, we have proven that Q0 and Q1 are distinguishable, and they need to be in separate equivalence classes. So we are going to pull out either Q0 or Q1. Doesn't really matter which one, because we know they're not the same. The question, though, is, are they the same as Q3? Are Q0 and Q3 distinguishable? Are Q1 and Q3 distinguishable? Because that will tell us, based on this set, what the final result is. Is there one state that's distinguishable from both? Or are two states the same and one state distinguishable? So let's look at Q1 and Q3 and Q0 and Q3. So Q0 and Q3, here and here, is really bad to do in ways that I can show and make visible to the class, but you're here and read a 0. Where do you end up? One ends up here, one ends up here. Q1 and Q2 are in separate equivalence classes. So we were able to show that Q0 is distinguishable from Q3 because on a 0, they end up in states with different distinguishability and different equivalence classes. On the other hand, Q1 and Q3, can we show on a 0, we end up in the same state, and on a 1, we end up in the same state. So we can't really say anything about Q1 versus Q3, but since we were able to show Q0 is distinct from Q1 and Q0 is distinct from Q3, that Q0 belongs in a separate equivalence class. So we're going to pull out Q0 and not Q1. So we're going to make a third equivalence class with just Q0, and we will remove it from this equivalence class. Since it's by itself, this tells us that we need Q0. Q0 is doing something here that is necessary for this DFA. Let's continue this process. There's this pair, which we just showed we can't really do anything about. There are these two, and we need to make this first pass. So Q2 and Q4, on a 0, we move here. And we know that Q1 and Q4 are in distinct classes. So this shows us that Q2 and Q4 are distinguishable. So that means since there's only 2 of them, we can remove either one from this equivalence class and make a new equivalence class. I'll pull out Q4. Why not? It does not matter here. Now that we have this process, we're going to loop back around where we need to consider every pair of states that are currently in the same equivalence class. There's only one left, Q1 and Q3. And we loop back around and do this pass through the loop because we made at least one change, pulling one state out of an equivalence class. As soon as we go through all of this process, making no changes, then we terminate. So we're gonna look at Q1 and Q3 again. On Q1 and Q3, on a 0, we get Q2 and Q2 in the same equivalence class. On a 1, we get Q4 and Q4 in the same equivalence class. We cannot show that Q1 and Q3 are distinguishable. And we terminate because there are no other pairs of states to consider. So that tells us that Q1 and Q3 are performing exactly the same logical process in this DFA. So it's equivalent to say now on a 0, move here, or on a 1, move here. Because 1 and 3 are the same. So we could just take this out, redirect this 1 arrow to here. Since this 0 went here and this 0 goes here, this 1 went here and this 1 goes here, this is all we've done. We just have to redirect the arrows of anything that comes into the state that is considered to be indistinguishable. Anything that comes into that should go into the other state that is considered to be indistinguishable. And now you have an equivalent DFA that removes this arrow, and this arrow. So states and all arrows into and out of that state. You're redirecting the arrows into and ignoring the arrows out of. Question?
Is there a reason we picked to get rid of Q3?
No.
You could do it the other
You
way.
could get rid of Q1 and redirect the 0 arrow here and get rid of this arrow, and this arrow, and that arrow. Redirect, since this is an arrow into here, we redirect an arrow into here. Getting rid of Q3 requires 1 change, since there's 1 arrow into Q3. Q1 would require 2 changes, because there are 2 arrows into Q1.
So since Q2 has an arrow coming into Q1, we'd have to redirect that incoming arrow into Q3.
Right, into Q3. Since these are indistinguishable, any arrow into one could be an arrow into the other.
Both ways.
Yep.
Okay.
Great question. How are we feeling about this process going through a single example? Question?
The arrow leads here to Q1, the 0, Q2 and Q1 neither happen.
Where would we put it otherwise? Or what would, this is basically saying we need to see 2 zeros, an even number of zeros from acceptance in order to accept again. Or a 0 and a 1. Once we see that 0 and a 1, then we can see anything and accept. But if we see 2 straight zeros, so we do need both of these just for that case of however it is that we got to Q2, we need to see an even number of zeros to accept, or without a 1. If it's ending in zeros, it needs to have an even number of those zeros at the end. Or a 1. I'll let people stare at that for just a little bit in case there's something that comes to mind about a question, this process. It seemed like we're kind of split half and half from my quick survey of the class on this makes sense, or I think this makes sense, and I at least get some of the idea, but not much of it. Yeah.
Q1 was to have an arrow pointing at itself, a loop, and you got rid of Q1. With the thing that you were replacing it with, would you have to add?
Yes.
Yeah.
Yeah.
In your equivalence classes, does it matter like at all moving the Q0 out or the Q4 to their separate classes?
It mattered when we did the Q0 and Q1. It did not matter when we did the Q2 and Q4 because they're going to end up in their own separate distinguishability. But when we found that Q0 and Q1 were distinguishable, it absolutely mattered which one we pulled out. Because imagine pulling out the Q1.
Could you have pulled out the Q1 and the Q3?
No.
Could you?
Oh, together. Yes. Yeah. But you needed to keep them together because they ended up being indistinguishable. Because we found that Q0 and Q1 were, in order to pull something out, it has to be distinguishable from every other element in that set. And not just once you discover a pair, pull out either one. It has to be that Q0 was distinguishable from Q1 and Q0 was distinguishable from Q3. Otherwise, if we pulled out Q1, we never would have found this pair, which we needed to find to be able to reduce the state.
So could you start at Q3 or Q1, or do you start? Does it not matter which one you start at?
Doesn't matter which sets you, yeah, that's what that loop exists for. And to give you a little bit of intuition of what's happening, this is basically looking backwards. One character, two characters, three characters, the W that we're using to find whether they're distinguishable or not is going to start looking at strings that become one character longer with each one of those passes through the loop. When we pulled out Q0 from this and couldn't see that Q1 and Q3 were distinguishable, that was distinguishable with length 1. But imagine that we had found, since we found that Q0 and Q1 were distinguishable, now if the question was, is this distinguishable on the next pass, we're now looking at characters of 2, because if we found that Q3 is now distinguishable from Q0 when it wasn't, I guess it was before, but if something was distinguishable now that wasn't before, it would take a string of length 2 in order to show or prove that distinguishability. But we're just showing with longer and longer and longer strings as we loop this, because every distinguishable pair that we found in the last iteration, we're looking at that many characters plus 1 for any changes that we would have made to this. If that changes whether these are distinguishable from each other, the fact that we pulled this out last time, that means that the string we needed to look at was 1 character longer. I don't know if that makes sense or not, but yeah.
Is there a way if you can just clarify your process for finding if it's distinguishable or not?
Yeah, so we're looking at, initially, we break these down into 2 sets based on their finality. All non-final states in one and all final states in the other. Then we're looking at all pairs of states within the same set and trying to show, is this state distinguishable from every other element of this set? So we looked at Q0 versus Q1, Q0 versus Q3, and you look at it for every single character in the alphabet. So this alphabet is 0 and 1. So we need to be able to show that there is, to show something is distinguishable, we find one such character, in this case, either 0 or 1, or both, such that when you transition on that character, you end up within 2 states in different equivalence classes. If the destination of that transition on both of those states leads you to 2 states that are in distinct equivalence classes, then we can say that that pair is distinguishable. And we can only pull it out if it's distinguishable for every element in that set. You can also, instead of drawing it out like this, draw it out like a table where we have, this would be a triangular table where we would have Q0, Q1, Q2, Q3, and Q4 on one side, Q0, Q1, Q2, Q3, and Q4 on another. We can say, I'm just going to put an X when we can show that they're distinguishable from each other. In the initial state, everything is distinguishable. We don't care about itself. So we just don't need that. We just need one of these because it's if Q1 is distinguishable from Q2, then Q2 is distinguishable from Q1. So we can ignore half of this. Which half do we want to ignore? Doesn't matter. So we're going to ask the question, is Q0 distinct from Q1? So we will start with just the equivalence classes. So we knew that Q0 was distinguishable from Q2 and Q4 because Q0 is non-final and Q2 and Q4 are final. For Q1, we said that it's distinguishable from Q2 and Q4 because difference in finality, and Q3 was also distinguishable from Q2, so we need Q3 and Q2, that one is distinguishable, and Q3 and Q4, that one is distinguishable. Do that a little bit too high. Q3 and Q4. So we had question marks here, 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 and here. So these were the pairs to go look at. If we can find that any one of these rows and or columns is all an X, then we can pull it out into its own equivalence class and stop looking at it. That would be the other way to look at this process. So you're going to go through all question marks, turning as many question marks into X's as you can. And then as long as you made a single change or more, you'll go look at it again, and look at it again, and look at it again, until you make no changes. And the end result of this was that we found that Q1 and Q3 were the only remaining question mark pair. So we're going to say that we did that work, we did that work, which pulled out Q0 into its own set. We did the Q2 to Q4, those were distinguishable, and I put a question mark on Q2 to Q2, doesn't matter. 1, 2, 3, 4. We're good. This was the only question mark that was left at the end. On termination, we can turn this check mark into a check that basically says those pairs are indistinguishable now because this process is terminated. And this is the knowledge that we gleaned from this process. We now know the distinguishability of every pair from starting from a bunch of unknowns. But since this check mark was there, we found that we could get rid of one of the states, since those were indistinguishable. Yeah,
Just to double check what you mean by distinguishability. Is it if the two different states go to same state on an input, or if they both go to a final state or not final state?
it's their own, in their own equivalence class. So it starts out being finality, but what we want to reference as we continue this process is the distinguishability classes, the equivalence classes we have here.
So if they end up in the same spot and they're indistinguishable. Like if
At least
you
we
do
can't
the-
show that they are distinguishable yet. If for everything they end up in the same, then yes, they are distinguishable. That is a way to shortcut this. If for every element of the caret, we actually saw this here, that on a 0, they ended up in the same state. On a 1, they ended up in the same state. That's actually proof that they're indistinguishable with length 1.
So would it also work if Q3, if it's one path, went to Q2? They're both still mapping to.
Yeah, we redirect this to here on a 1 rather than that.
Yeah.
Yeah, so in this case, it was Q1 and Q3 that weren't distinguishable. Since this is final,
Oh, it doesn't matter, yeah, they both have.
initially they were in the same equivalence class, but on this path, on this first path, we broke Q2 and Q4 out. So it would look like they're in the same equivalence class, but when we look at this pair, then we break them off to say that they are distinguishable. That's why when we loop back around on the next pass, when we follow the 1 from here to here, yes, they're still final, but now they're in distinct equivalence classes. And now we can say that Q1 and Q3 are distinguishable in this version with a 1 pointing here.
Okay.
That's a great point and a great way to show or draw out why we need to loop this multiple times. When we make a decision that 2 states are distinguishable, if we had looked at it before and they looked indistinguishable, now that information may make the next thing backtracked with 1 character longer look distinguishable. How we doing? Show a thumbs now, maybe this has helped a little bit, maybe not. Like they're coming up a little bit. Little bit, more work needed. That sounds about right. Anything else that I can say about what's on the board before we move on? There might be one more example, I actually forget. Yeah,
So we're looping through the pairs and then with each pair we loop through the alphabet? Or is it
Yeah.
one chart and then we go back to a different pair and test?
no, you're looking at every possible letter or symbol in the
For a
alphabet
pair at a time.
for a pair at a time, until we find one that shows that they're distinguishable. We don't have to look at anything else once we show that they're distinguishable.
Okay, and they're distinguishable and then different equivalency classes.
Yeah.
And you're gonna have to make another one.
Yeah.
I'm gonna have to implement this.
Yeah. This would be a good lab. If I continue to want more labs in this class, this would be something that I think would be a good lab for the class. Anything else I can explain before we move on? Okay, it's gone. Obviously, I'm happy to continue talking about this in office hours, assuming there are no further. There has to be some other reason. So we went through this whole process. I draw it out, I write it out on the slides. I fix all of this. But this should just be the words of what I just described in case this helps you to make more sense, or you're looking back at this at a later date. And then we also talked about what happens when we construct the minimal DFA. So redirecting arrows into one of those states that's indistinguishable can all be rerouted into the other state that is shown to be indistinguishable. If you want to represent what that state's name is, you can now, if you had something like a Q0, Q1, Q2, Q3, you can now combine them. This shows that I combined states 1 and 3 together. And the new name for it is 1, 3, the old 1 and the old 3, because we didn't need both of them. And it's a much simpler DFA. Takes a lot less memory. I actually don't have another example of this. So I can pull some examples out of textbooks. This would be a great thing to do either on a review day or I will always let the class dictate if this is something that we identify as a general weakness or something that we'd like additional content to cover beyond whatever is assigned for homework, let me know. And I'd be happy to find those extra examples and make sure that we cover the material that helps cement the most knowledge that we can get out of the time that we have. Any other questions before we move on to the next topic? Right. We'll go do it. I tend to make pretty short slide decks, but then I make a lot of them. I think there are 23 of them for this class. But we're going to dive into regular expressions because this is an equivalence to something that people have seen before. So as I always do with my slide decks, we start with some motivation. And that is that we can describe regular languages in actually quite a number of different ways. We've talked about how one of them is by constructing a DFA, one of them is by constructing an NFA. But there are two more that we're going to find. One is a regular expression and one is a regular grammar, which is like the grammars that you've been working on for your first homework, but they have some additional restrictions to them. So we're going to focus in on regular expressions first, and then we will cover regular grammars. The syntax for regular expressions in this class is going to be a little bit different from the syntax for regular expressions that you might have seen before if you have seen these, but they have the exact same computational power. And the reason that I use exactly this notation is it is the formal notation as well as the notation that the textbook uses. If you're curious about how to take this and apply it to regular expression construction in code, in finding text in a browser or in a text file, let me know and we can make that connection. So we have, as allowed in a regular expression, you can use any characters in the alphabet. We can also use parentheses to override an order of operations that I will talk to you about. There are operators, just like mathematical operators or logical operators. These are going to be logical operators as well, or repetition-based or concatenation-based. So the operations that we'll see are like that. Concatenation, repetition, stuff like that. So the symbol plus in a regular expression is a set union operation. You can also think of a union operation as a logical OR. We will use the star or nothing, like the dot or a star or nothing to represent concatenation. I generally write it as just nothing. So if an A and a B appear right next to each other, they're concatenated. We have a superscript star for star closure. This tells us of the preceding section, we can repeat that 0 or more times. just like we've seen star closure for everything else that we've seen it in this class so far. And that's it. That's the entirety of the operators and everything that is allowed. If you construct an expression out of the characters and strings that are allowable in the alphabet and parentheses and these three operators, you can express any regular language. And you will not be able to express any language that is not regular. If you can draw a DFA for a language, you can also write an equivalent regular expression for that language. If you can write a regular expression, you can also find an equivalent DFA. And we find that this is very frequently used outside of just theory classes. So complex search functions in any text editor or browser, and becoming more and more popular in general games as well. So I study games a lot. If you have a shared stash or a large stash in a game, very frequently the search fields in that allow for regular expressions. So I play Path of Exile a lot, and Path of Exile allows you to do things like search for items via modifier values. Modifier, if you're looking for some amount of a damage roll between 100 and 150 increased percent, you can do that. If you're looking for the particular socket lineup of at least 3 linked sockets and they're all distinct colors, you can do that. And it will highlight just the items with exactly those properties. So becoming more and more useful. If you know regular expressions, it's very useful to gain slight edges in competitive games. So Path of Exile does it. But let's give you a very simple example. So here's a language with the alphabet of A, B, and C. You could come up with a regular expression representing a language in this that says A union BC, and that whole expression repeated 0 or more times. So this says the star closure of A union BC, if you wanted to write this in English. Let's come up with some strings in this language. What is the shortest string in this language? I should say sentence. What is the shortest sentence in this language?
Did you feel like ABC or A?
Neither. Good guesses though.
Nothing.
The empty string, yes. Since it's the star closure, it says 0 or more of what comes before it. What comes before it? This entire expression. So if you have 0 copies of A union BC, you get the empty string. So we can start to identify our language as we know the empty string is in it. What is the next shortest? A, yes. So you know from a union, you can take basically the star closure is going to say we can take from one or the other of both of these any number of times. So I'm also going to say that this right-hand side is length 1 for the moment. Even though it's 2 characters, we will say that BC comes next as something that is coming from one side of the union or the other. Now, if we wanted to come up with all combinations that utilize 2 of these, we could say one of them is AA, one of them is ABC, one of them is BCA, and one of them is BCBC. Do people understand how I got to this point? So now we would continue this process with 3 copies of these. So we would have AAA, AABC, ABCBC, BCAA, BCBCA, BCBCBC, etc. So this continues infinite. So we end up with a very long infinite language, but we have some way of understanding the structure of this language coming from the star closure of this. And we can represent that logically via a regular expression with that syntax. Questions on that? We can also think about allowing for recursion here. So when we say 0 or more of something, you can either terminate it or you can continue to add it. This is why all of this is actually related. The grammars that you're working on for homework have some similarities to recursion. The DFAs that you're drawing, if you draw a loop in that, it allows for some recursion. It's also similar to constructing mathematical expressions, in that we can utilize some primitive regular expressions, just like we have primitive data types. These primitive regular expressions would be the empty set. Lambda, representing just the empty string. Some character in the alphabet. And then we could say, if we have two primitive regular expressions, we can combine them or associate some rules with them such that we can, if we have R1 and R2 as two different regular expressions, then R1 union R2 is also a regular expression. R1 concatenated with R2 is a regular expression. The star closure of R1 is a regular expression. And R1 with parentheses around it is the exact same thing as R1, but that is also a regular expression. So now we have the ability to piece together parts of primitive regular expressions to make more complicated regular expressions. So just like with math, you have numbers, you have operations you can do on numbers. You can define your own order of operations by overriding the default order of operations with parentheses, and you can construct an arbitrarily complicated mathematical expression out of the individual pieces of what's allowed and how can you combine the smallest pieces of what's allowed. So it's very much like math in that sense. It's just a way of building up the logical representation of a language instead of an expression that evaluates to a value. We can say that a string is a regular expression only if it can be derived from primitive regular expressions via some finite number of applications of the associated rules of bringing them together. Questions on kind of the formal definition here of a regular expression? All right, so we can say that the empty set is a regular expression denoting the empty set. We're just still going to call that the empty set. That's a regular expression with no elements. Lambda is a regular expression denoting the set that contains the empty string and nothing else. For every character in the language, there is a regular expression just denoting the set that contains that character. And then we can combine them. If we say in the language of R1 plus R2 in regular expression language is the equivalent of saying, let's take the set union of the two languages, L of R1 and L of the language of R1 and the language of R2. We can do the same thing with concatenation. It's the same thing as concatenating the two languages together. If we put parentheses around it and it's by itself, we can just take out those parentheses. So 2 parentheses is equivalent to 1 parentheses. 1 parentheses is equivalent to 0 as long as the language is an associated simple expression. The same thing with the star closure. And this allows us to do things like take a regular expression and simplify it in the same way that you might simplify a mathematical expression. So we can go through a lot of the same logic that you would with math operations when thinking about regular expressions. It's really just another function type. So the first 3 cases are base cases for recursion, and then you can allow you to find simpler components recursively. Tomorrow, we will come back and look at how to read regular expressions and also how to convert and find the ability to modify regular expressions, converting them into other forms that might be simpler, might be easier to work with, easier to see the equivalence of 2 languages by morphing one language's regular expression into another language's regular expression to show equivalence. So we will hit that up tomorrow. I have office hours starting now for at least the next hour, depending on demand.